So let us understand it slowly. So basically, what you know, proton has spinning nucleus. So let's say this is the nucleus. So it will have two spin. One will be clockwise. This is clockwise. This is anti-clockwise. So the first statement, what? The proton has spinning nucleus. So these are spinning nucleus. Spinning nucleus. Then what happens if the nucleus spins? It possesses a positive charge. If a charge spin around its axis, it will generate a inherent magnetic field. So spinning nucleus has these have inherent magnetic field. Inherent magnetic magnetic field because of spin. What type of spin? This is nuclear spin. Nuclear spin. So what will happen? First, let's say this is simply a proton nucleus. So it has been, so basically these two states are degenerate, whatever. So these two states are degenerate, means they are equivalent. You cannot identify them. These two states are degenerate. You can tell that this is at plus half, these are minus half. So now these are degenerate. Let's say we have these two spin. Means just here this I am just representing axis. I'm just along this axis it spins, but this is not the direction of the spin. That's why it is same. This is plus half. This is minus half. Basically, this is the axis of spinning axis. Along this axis, for example, it goes in clockwise directions. It goes in anti-clockwise direction. So these two are degenerate. So we cannot identify it. It's same energy. Same energy. Now, after this state, if we apply a strong magnetic field, let's say this is the strong magnetic field we have applied, B0, then what will happen? Now, these are degenerate, and as this is an inherent spinning nucleus, it has some magnetic field, that is inherent magnetic field. So this inherent magnetic field will interact with the external magnetic field. Inherent magnetic field means inherent magnetic field means it's a magnetic field that generates from the spinning of nucleus around the axis. So inherent magnetic field will interact along the with the external magnetic field. Then what will happen? So basically, let's say this is the external magnetic field. So this is a state where the spin of the nucleus align along the magnetic field. So this is the low energy level. This is low energy level. Means so this align align along magnetic field. This another spin, what will happen as these two spin are opposite, so this is align against the applied magnetic field. Align against the applied magnetic field. So basically a simple phenomenon happens. This is energy. Energy means energy, this axis, and this is nothing basically. And here we have applied our external magnetic field. So what happens? These two states, that is plus half and minus half, was degenerate, and they have some inherent magnetic field because of spinning along their own axis. Now, as we have applied a strong magnetic field, external magnetic field, now the degeneracy breaks and they just produce two energy level. So here this align along the axis, this align opposite axis. So we just, it was degenerate, degeneracy break, the two energy level generates. Now what we have to do, we will check the what is the gap, the value of extent of their differentiations, what is the gap. Then we will apply a external wave or the external energy. If that energy exactly matches with this energy gap, then the nuclear transition will happen. That's from this state, nuclear will go to this state. Basically, what we are doing, these are degenerate. We break the degeneracy by applying a magnetic field V0. This is done, separate. Now we are just allowing the nucleus to absorb some radiation. If the radiation that we are providing exactly matches with this gap, then the nuclear transition will happen. So this will create, or this will causes nuclear transitions. Nuclear transitions. And this is the basic principle of NMR spectroscopy. How NMR is recorded, we will not go to that part because of time, but this is the basic things. So, at which ranges this energy gap lies? Basically, this external energy lies in the range of radio frequency region. Radio frequency. So let us just summarize these things. Very simple things. Nuclear has a spinning. A proton has spinning nucleus. So there's two spin. One is plus half, minus half. Because of the spinning nucleus, they have inherent magnetic field. This inherent magnetic field or the spinning, they are degenerate. You cannot identify which is plus half, which is minus half. But if we apply an energy, external magnetic field, then the proton nucleus with plus half, this will align and will have low energy, and the spin with the value minus half, this will opposes the external magnetic field and will have high energy. So the degeneracy breaks into two energy level. Now from external we are supplying one external frequency, means radio frequency, because the radio frequency matches with these things. The frequency that matches means it's a resonance conditions. Once the frequency, external frequency matches with the internal one, the resonance happens and the nuclear transition happens. That's why nuclear, this is happens on nuclear state nucleus, it induced by magnet, nuclear magnetic, and the resonance. That's why the name nuclear magnetic resonance. So it's clearly, now we have, I hope every student have visualized very nicely, like a story-like manner, the basic principle of resonance. Then, and one thing we'll remember that the external frequency that we use are in the range of radio frequency region. Sometimes this is asked in MCQ manner or something. Just okay. So, as we are not discussing in a very depth manner, means just we'll try to analyze the spectra. We are not going something. So basically, which type of protons is there from the chemical shift we can tell. I am not telling in details what is chemical shift. So basically, if we see the NMR spectrum, let's say this is the spectral line. So this is 0, 1, 2, 3, then just cut it. Let's say it is 7, 8, 9, 10, 11. So it is in ppm. This is called delta in ppm. This is called chemical shift. Chemical shift. So because of different nuclear transitions and something that I am not details how it is recorded, we get the output. Just I am telling that because of different nuclear transitions that originate or arises from different proton environment, we will have different peak. So from this peak, we can say or we can predict the nature of the protons. So first thing what you will say for examples, we have a protons, this 11, let's say we have NMR signals. In these regions, we have one proton like that, and in between here around 2, we have a proton like that, signal like that. So let's say this is the NMR spectrum. I am using telling spectrum because this is singular, only when you speak. Okay. Now, when you will run the software, you will understand we have to integrate. If we integrate this value is going to be 1 and this value is going to be 3. It indicates that the number of protons is 3 times than that of these ones. So basically what? So this is, say for example, CH3, the double bond O, OH. This is for OH protons, and this is for CH3 protons. Look, the number of protons is 3. That's why its intensity 3 times than that of this. So from the integration, we can say the number of protons. This is very valuable or important statement. From the from the integration value, we can say or we can predict the number of protons. Now, so here I am not telling about which range which proton it comes, but later when we will discuss the problems, different things, there in depth we will discuss which protons is coming and at which range. At that time we will discuss that this is that protons, and because of, for example, we know that aromatic protons come around 7. We'll discuss it during that times. Later, rather, we can say a lot of information from the NMR spectroscopy. Let's say we have some atom and let's check their electronegativity. Electronegativity. This is highly interesting, this part. And think about the compound and their chemical shift in 1H NMR. Delta value in 1H NMR. Let's say it's a lithium. We no need to memorize the value, but just for our example, we are seeing its electronegativity is 1. Let's think this. So this is highly electropositive complex. We will have a huge negative environment here, huge negative environment. As a result, this will shift to the low ppm value. So its basically its value is minus 1.94. So the protons become, as if the proton is more electron rich environment, if the proton has more electron rich environment, it will shift the lowest ppm value or lower ppm regions. We see this will exist a lithium plus and this is minus, the huge negative environment. That's why it's, see the ppm value 1.94. Now shift to silicon. Its value is 1.9. Let's think about the complex CH3 Si, this tetramethyl CH3 whole 3. The standard is value is 0. We'll compare with these things. We normally consider this as 0. Then with respect to this, we say the value. Think about nitrogen. So its electronegativity 3.0. Again, I am saying we no need to memorize this value, but we are correlating here. Let's have a think about this complex compound CH3NH2. It is electronegative, so it will hire the electron from these bonds, as it will be delta plus. So some electron deficiency is there. If it is electron rich, it will go to the negative region or the lower ppm value. If it is electron deficient, it will go to the high ppm values. That's why it will arise along 2.1 ppm, delta in ppm. Okay. Oxygen. For oxygen, it is 3.4. So what will expect? Let's say methanol. So oxygen is more electronegative than nitrogen. So OH group makes this methyl group more electron deficient than that of what the amine do. This is electron deficient, more electron deficient. So here the value will come at more higher ppm value. Look, 3.5 ppm. How much is interesting this is? Think about fluorine. This is the highest electronegative, 4.0. CH3F. So these values will be highest. This is the highest electron deficient among these three. This is the highest electron deficient methyl, as fluorine is highest electronegative. This is the lowest electron deficient. Means indeed it's electron rich. It's not deficient. So here this proton will appear at the highest ppm value. This is 4.27 ppm. So from these values, that we are correlating the electronegativity has a significant role in. So where we are just discussing these basic things, because if we have the clear-cut concept, crystal clear concept, then we can solve the problem easily. So basically, we should have very clear understanding of the NMR spectroscopy. That's why we are just doing this kind of fine tuning. Basically, it is very much easiest and beautiful spectroscopy, but people think that very much tough. This is due to the fact that the basics is not clear. That's why we are putting so much emphasis in the basics levels. So electronegativity is a very much important parameter for different chemical shift. So wait a bit, just I'm coming in a seconds. Do not leave, then we cannot record it. Now, so whatever the discussion we have done up to now, based on that, if I ask, so can you predict the relative chemical shift for CH3, Cl, CH2, Cl2, and CHCl3? Look, here the structure is like that. C, let's say it is Cl, we have three protons here. So this carbon is attached to one electronegative atom, so it will have electron deficiency. Here carbon is attached to two electronegative atom because chlorine is electronegative. So here the proton is more electron deficient. Methylene proton is more electron deficient than this. And here the, let's say I put the proton here. So this is highest electron deficient. So it will appear at highest ppm value. Highest ppm value 7.29 or 27. So remember this value. So when you will do your research, you have to do the NMR recording with CDCl3 as solvent. At that time, you will find that. So this is a value. There every day you are going to familiar with this value 7.27. Among these three, this will have lowest ppm values. It is 3.06 ppm, and this is the medium one ppm values 5.30. This is due to the fact that ppm, this proton is highest electron deficient. Then this one, because this proton is electron deficient because of these two chlorine and Cl atom, and this proton is among these three, it has a better electronic environment, as these three protons attached to one chlorine via carbon, two protons attached to two chlorine via carbon. Basically, I don't say that attached to chlorine, but attached to carbon, attached to chlorine via carbon. Okay. Now, dear students, if I ask a question based on the discussion, let's say, yeah, this is the molecule. This is methyl. So if I ask you how many methyl proton you will observe, how many methyl peak? Basically, the reply is that okay, these are equivalent. We will expect one methyl peak because these are equivalent. So we will expect normally one methyl peak. But one phenomenon happens there, that is resonance so much powerful technique. Now you will realize after this class, this electron delocalized there. We will have this kind of delocalized structure CO minus H. Because of such delocalizations, we will have this double bond character. Basically, in double bond C character. If there is single bond and if we have a rotation about single bond, let's say the group is like that, rotation about single bond, then these two will be identicals. We'll get only one. So because of this C double bond, N double bond C character, restricted rotation, it cannot be rotate. So now the methyl group have environment to environment. This methyl group have environment closer to oxygen. Sorry, this methyl group will have environment closer to hydrogen. Because of two different chemical environment, we'll expect or we'll have two separated methyl peak. Methyl peak. That's very interesting. Also, it's proof that yes, this kind of electron delocalization happens. That's why if it would not happen, then there is a rotation about these NC bonds. As a result, these two methyl group would be equivalent, but this is not happening because of this resonance, it has some double bond character and the rotation stops. So it will resolve into two different methyl. One have equivalent one will be closer to this O minus, one will be closer to H. That's why we will have two separate peaks. Based on this discussion, we can explain very nicely. Now, I'm going to share with you another fantastic story. I hope you will greatly enjoy that. Let's say, yeah, this is an alkene. For alkene, the chemical shift value mainly arises around 5 to 6. Let's say for this the value is 5.68 ppm. So you no need to remember the value, just only range is enough, around 5 to 6 the alkene proton appears. Now if I ask you, in benzene we have 3 double bonds, then for benzene also we'll expect this value around this region because it is double bond also, but this appears at around 7 to 8 ppm. For benzenes, the value is like 7.27 to 7 ppm. Now the question is why it happens like that. Benzene, it has 3 double bonds, so we could expect it will be like 5 to 6, but rather it is 7. So why this is this much shift? That will explain in these things. So, for example, we have a molecules here, let's say benzene. We have exposed this benzene to the external magnetic field. External magnetic field. Then what will happen? It's a normal phenomenon. If I do something against somebody, for example, if I knock a guy, the guy is going to fall down. Before that, the guy will try to resist himself or herself because he'll just try to push back. That's the main thing. If I apply some changes in a molecule, the molecule orient in such a way that the changes become minimum. This is the normal phenomenon. So I have exposed this benzene in an external magnetic field. So benzene will try to resist itself from this external magnetic field. So how it can do? So basically, benzene has a circular pi electrons cloud. So there's a ring current around the circular pi electron cloud. So let's say this is the benzene. This is the pi electron cloud. So ring current will maybe these directions and this also maybe these directions. Now the question happens, these directions ring will these directions or this direction. Now the question happens, now you just guess or remember the benzene is on the or perpendicular to the screen of these mobiles. There it is rotating on the screen anti-clockwise. If this is anti-clockwise, then what will happen? The external magnetic field will be in these directions because in that case your finger is up toward these directions. So this magnetic field, sorry, not external, this magnetic field will be these directions. So what we will try to do, the ring current will be such a manner that because of this ring current, a magnetic field will be produced in this way. Means it is opposing the external magnetic field in this fashion. It means that it is opposing the external magnetic field. Okay. So basically because of, let's do it here clearly, very much interesting things. So there is a ring current. Because of this ring current, let's say it is external magnetic field. This is external magnetic field, and we have this, yeah. So basically, this is ring current, and this induced magnetic field. Induced magnetic field. Magnetic field. So the flux, magnetic flux, is going to penetrate the benzene ring and coming in opposite side in this fashion. Now look, if we have a CH hydrogen is there, what that CH hydrogen is gaining? That CH hydrogen is getting a part of this magnetic field, induced magnetic field. So basically, what this proton is feeling, this proton is feeling the external magnetic field, let's say B0 plus magnetic field of this induced plus induced magnetic field, let's say be induced in which fashion? In the same directions. In the same directions. In the same directions. So basically what we have done, we have applied a magnetic field V0. Because of the ring current we have some induced magnetic field. Also it goes in this direction. That's why the proton gets the part of this induced magnetic field in the same direction. Basically, now let us visualize what is happening. So in presence of B0, let's say that two nuclear states supposed to separate this much in presence of B0. So as because of we have some induced magnetic field, now this separation will be quite higher. So this is for B0 plus B induced for. So their separation will be larger. As the separation will be larger, so I didn't discuss the technique in details, but believe me, if the separation become larger, then they will come to the higher ppm values. That's why they will come to the higher ppm values. So it will shift from 5 to 7s. As a result, the protons shift from 5 ppm to around 7 to 8 ppm. So basically what we understand now, we understand that much is that we have applied B0, and because of this induced magnetic field, this proton experience quite higher magnetic field. B0 plus some part that is B induced that comes from the induced magnetic field because of ring current. That's why this value shift from 5 to 7 to 8. I hope this part is totally cleared by you. So if you ask why the magnetic field direction is like that, because it will try to resist the external magnetic field. That's why its main component opposes it. Once it is going to oppose thing, then here it is going to oppose, but here this is going to, it will be circular. So if it comes in this direction, it is going to oppose. When it comes outside, it is aligning the sage. That's the beauty. Now you can ask why this is circular. As the ring current is circular, that's why the field will be circular. That's why it's circular. Basically, its role is it wants to oppose the external magnetic field. That's why the things is like that. So here we have ring current. Okay. Now see another good observations. If it is true, then what is happening for these things? Just we are making it bold to emphasize that this is on the front side of U. Basically, this is a benzene ring, and we have this kind of things, answer type of complex. Let's see it like that. This kind of complex. Let's think. Or also we can have better drawings with one more carbon atom. Yeah. Here we have two protons, H, H. Basically, think about the position of this proton. These protons just above the pi system. These two protons just above the pi system. Above the pi system. So put the molecule In external magnetic field, B0, there will be a ring current, and because of ring current, we know that if this is ring current, we will have this kind of induced magnetic field. So this is induced magnetic field. Look, these protons is falling in such a magnetic field that is opposing the external magnetic field in these directions. Look their positions. Just there are the pi systems. So they are on the opposing field. So you have given B0 to them. So let's say in the presence of B0, they are supposed to have this kind of splitting, but their situation or position is like that, they are getting a real magnetic field that is like this. Means B0 minus B0 minus B induced. B0 minus B induced. I said earlier that if this value become larger, it will come higher ppm. This value is very much smaller. That's why it comes around negative ppm. So this is highly desilting. Highly shielding. Basically, it's about 0.65 negative. Can you imagine? So if we say that the value is significantly low or value is just ignorable, this ring current is not. Ring current has significant value. It is making this proton negatives. This proton is aliphatic proton. It's supposed to come around 1 to 2 ppm. So 1 to 2 ppm it is making its negatives. So it has significant induced ring magnetic field. So significant induced magnetic field. Magnetic field which opposes the external magnetic field. So this is just their situations, positions. Their position makes them enable to feel the lowest exact or actual magnetic field. That's why this is very much interesting things. VVI. I hope you have clearly understand that. This photon is supposed to appear around 1 to 2 ppm. This is at 0.65 ppm. Okay. Now, for examples, we don't know anything. Just in lab, anything means we don't know the different electronic effect of different functional group. That nitro group is very much electron withdrawing, or the CH group very much electron withdrawing, or cyano group is very much electron withdrawing. We have recorded in NMR. Because of that, we are trying to put some conclusion. So let's say again, I am saying this question is not asked in CSIR net or GATE, but again we are practicing it or discussing it because of our so that our concept become crystal like clear. Otherwise, we cannot tackle the problem. And this is the only platform where you can now understand the NMR. Okay, so this is H. What we know that nitro group is electron withdrawing by two factors. One is minus R and minus I. So because of two nitro group, this ring become electron deficient. Electron deficient. As the ring is electron deficient, definitely this proton will be electron deficient. Electron deficient. In benzene, what happens? This proton is supposed to come around 7.25 ppm. And here the value is 8.48 ppm. No need to remember the value, just for our practicing purposes. Look, the ring is significantly electron withdrawing, means electron deficient. If we have to acid group COOH, COOH. Till now, we have read in book or we have been told that nitro group is electron deficient. Here we are getting direct proof from NMR that yes, nitro group is electron deficient. That's why the protons become electron deficient and it appear at higher ppm values. So nitro group makes the ring electron deficient with respect to benzene. We also know that the acid group is electron deficient. So look here the value. This comes at 8.10 ppm. We also know that cyano group is electron withdrawing C triple bond N and C triple bond N by minus R and minus I. This is proton 1.80 ppm. So if somebody asked, can you make a comment on COOH and CN functionalities from this NMR value? Yes, of course we can make. Look the value 8.10, 8.10 means the acid group and cyano group is equally electron withdrawing. If somebody asks, can you make a comment on the electron withdrawing ability of nitro group and acid group? Look, the value is 8.48 ppm. Here the value is COOH, 8.10. It means that nitro group is most or better electron withdrawing than acid group or than cyano. And and acid and cyano, they are equally electron withdrawing. Then we'll see the value for aldehyde. Aldehyde. Aldehyde also electron withdrawing. Its value is 8.07. So aldehyde is better electron withdrawing than nitro. So if we want to do just a comparison with electron withdrawing power or ability, so nitro is the most electron withdrawing, then we will have aldehyde, CHO, then we will have acid and equal CN. These things we can conclude from these discussions. So see, now you realize what are the fantastic phenomena happening here. Whatever the electronic phenomenon you have read from book or you have been taught in class, there was no proof. Here you are getting the proof. Yes, it is happening. First of all, you got the proof there that resonance happens. Because of that, two methyl peaks separated that I showed earlier. Now you can ask, sir, so can you prove that methyl group is electron donating? Yes, if that is true, if we have methyl group, then we can argue with that. Then this ring will be electron rich. Electron rich, as methyl group can push the electron through by plus I effect. Yes, so look at the value of these protons, ppm values. It is 7.03. Look, with respect to benzene ring, now this ring is electron rich. It is also fantastic things. Now you can say, so sir, what will happen for these things? We know that CF3 group is electron withdrawing by minus I. CF3 electron withdrawing by minus I effect. So this will be electron deficient ring. Electron deficient. As a result, this proton will appear at higher ppm values. Means it appears at, you no need to remember, around 7.0 something, around higher ppm values. 7.9 or 8 at that range. It is electron deficient. So from the discussion, we can say the different electron withdrawing ability of different functional group, as well as we can correlate them. We can predict them. Based on this discussion, we know that if they become electron deficient, the ring become electron deficient, the proton will have electron deficient environment, it will shift to the higher value. Then we realize that okay, then if we put or install two methyl group, the ring is going to be electron rich, then we could expect or we can expect the lower ppm value with respect to benzene. Yes, indeed that is happening. It has 7.03 ppm. This kind of fantastic story or phenomenon that we can explain from these things. Another thing I'm going to say it here, let's say this is alpha beta unsaturated carbonyl. Alpha beta unsaturated carbonyl. Basically what? This is some alkene. If this is an alkene, the peak we will expect around range 5 expected. But see what happens. You know that if we have an alpha beta unsaturated carbonyl compound, this kind of delocalization exists. As a result, minus, this is plus. Look at these protons. This is attached to electron deficient carbon. So this proton will have high electron deficient in environment. High electron deficient environment. And looks its ppm values. It's appear around 7 ppm. So being as alkene, we could expect it will come around 5.5 region, rather it is appearing 7.7 region. So these kind of things also that we have been told or you read from book that there is this kind of delocalization, also you can get it from NMR also. The NMR value tells that okay, this proton is attached to a electron deficient carbon atom, and that electron deficiency is coming from the delocalizations. Rather, at last, when we sum up after the discussion of every spectroscopy, from IR also you can give a try. So if there is no delocalization, this carbonyl was expected to be stronger one. Because of this delocalization, this is getting some single bond character. As a result, this C double bond O become weak and its IR stretching frequency decreases. That we will sum up later. So that's, I always put emphasis on spectroscopy part. It is that thing which proves you what you have written, what you have read. And also, if this is true, then you can argue, okay, sir, if I put one nitro group here, then what is going to happen? If nitro group is here, then also this kind of delocalization will take place. Then we will have this kind of environment plus, this is plus, so it is highly electron deficient. Electron deficient. Its value comes at the region 7.3. And look, we know that electron withdrawing efficiency of nitro is more because of minus R, as well as nitrogen itself electron withdrawing by minus I effect. But we are not going to that small change in value, but rather we can understand this phenomenon is happening, this type of delocalization happening here. That's why in spite of alkene, its signal arises in the aromatic regions. Then now one other counterpart will come. So if we furnish or install one electron donating moiety here, then what is going to happen? Then we will have this kind of delocalizations here. So this is double bond N plus H minus. Now look, this carbon became electron rich. As a result, this proton environment also become electron rich environment. electron rich environment. So it will come at lower ppm values, and this value is delta is equal to 4.4 ppm. This is delta. I should use delta for perfect scientific term. In bracket, of course, in ppm. So alkene protons is supposed to have a value like 5 ppm or 5 to 6. When I'm installing an electron rich or plus or moiety that can take part in delocalizations, its value is just 4.4. Now you can easily understand by closing your eye easily. Okay, the phenomenon I have read in book. Now I can totally visualize in terms of NMR spectroscopy. That's why you should always thank to this spectroscopy. Thank you NMR spectroscopy. Because of all this spectra thing, you can understand clearly such type of electronic environment. I hope you are greatly enjoying this topic. Okay, in the next part, we'll discuss the coupling of NMR, because the coupling is a fundamental or very sensitivity technique inside NMR. Analyzing this coupling, you can say which kind of proton is attached there and the number of protons. As this is very much fundamental topic, in this class I will not elaborate it that much. We'll fix this in very basic level. After that, gaining knowledge, in the next class we'll see how to determine structure by NMR spectroscopy. Here we'll analyze, or we'll try to realize why the doublet appeared. What do we mean by doublet, and why at all it comes, and why triplets at all come. That kind of things we'll realize here. I think you are gaining very nice concepts. If you are interested, then you can read a book of Clayden, because I am just teaching from that book because it is nicely written. And then I will cover up different example from another kind of book from Carey and Sandberg and something more, and some question papers. So basically, the chapters you should learn most in chemistry, at least at master degree level, that is nothing but the spectroscopy. That's why I'm taking so much time in spectroscopy. I know that much amount of question will not come even from spectroscopy. Only two questions will come. But nowadays, what is happening? They are relating spectroscopy to each and everything. Even they are relating spectroscopy to the stereochemical problem. They are relating spectroscopy to the synthesis part. That's why we should have very basic, clear understanding about this thing. That's why I'm going very much slowly with this spectral analysis. Okay, let's think about these molecules. Just we won't look at the other part. This is NH2. Yeah, this is HX and this is HA. Here, just two protons will look. See, we see that if we have a nearby one proton, it makes it doublet. So one proton is here, one proton is here. So it will appear as doublet, it will appear doublet. Now we'll try to analyze why doublet. Why doublet? It's very to analyze. See, it's a proton, so it has one nuclear spin. It will also have one nuclear spin. So here what we are trying, what we are trying. So how does the nearby protons or magnetic field of proton influence this magnetic field? So basically, this proton, what will have? This proton have, there are three components. This proton have inherent magnetic field because of its nuclear spinning. It experiences external magnetic field plus the magnetic field coming from this part. There are three components. So component one is external magnetic field, external This proton will experience external magnetic field plus, let's say, HA. So HA have some inherent magnetic field. So HA inherent magnetic field plus the magnetic field from this neighbor HX. Magnetic field from the neighbor HX. There is a playing or talking between these three components. Just we have to resolve these things, and it is very much easier. Now, again, I am telling just to clear it, just to be a visualization that there are three components: external magnetic field that is facing this HA plus its inherent magnetic field that comes from its own nuclear spin plus the magnetic field from these neighbor protons. Now you'll see the battle or the interaction between them. What is happening? Let's say this is Hx, the peak from Hx, and this is the peak from Ha. If there is no interaction, so they will be like that. So no interactions, no interaction between Ha and Hx. Now we'll consider the interaction. Definitely, they are experienced in the presence of external magnetic field. Yeah. Now we see what happens. External magnetic field. Yes. Look. Now see the nuclear spin of Hx align along the external magnetic field. Okay. So this is the magnetic part from Hx. Let's write Hx in bracket. So what HA is facing here? So basically HA is facing here. HA is facing very basics, nothing non-understandable, very basic, easy to understand, easy to visualize. What H is facing? External magnetic field B0 plus this part that is aligned along the directions of magnetic field of Hx. So you have given an external magnetic field B0 and H is facing quite more than B0 and quite more part that comes from its external magnetic field or neighboring magnetic field from HX. So if HA would not interact with H, if HX had no influence on HA, then the peak was supposed to come here. As I taught earlier, if the magnetic field is stronger, the splitting between two nuclear state will be larger and they will be shifted to higher ppm values. That's why this Ha now comes here. Why it comes here? Because it feels that magnetic field B0 plus Hx as it's aligned. I hope you clearly understand these things. If it if do not interact with Ha, then the peak was supposed to come here. Now think about these things. Another thing is there. B0 external magnetic field. If we did not interact, the field was supposed to come here. Now this is HA. Now its nuclear spin opposing the external magnetic field. Then at is opposing what the value of actually HA experiencing. So HA now experiencing or facing, let's say face also, facing B0 minus at it is opposes B0 minus this much amount from HX magnetic field. Magnetic field. That's why the value is quite smaller. Here the value, if we just split the value, no interaction is only for B0. This is only for B0, and here it will be quite small B0 plus this part, let's say HX. Here this quite smaller, that is B0. Actually, I should not write B0 plus HX here, so that's I'm erasing the value here. So this splitting is from or because of the component B0 plus this contribution means aligned along the magnetic field of HX. So this is, again I am erasing this part, and this part is basically for B0 minus this part HX. So now the peak will come here HA. So one is for the contributions or the interaction when HX align along the field, when HA align opposite to the field. So if we took the resultant of these two, the resultant will be the exact spectra. So this is for this part and this is for this part. So if there are no interactions, we supposed to get only one value of HA, but because of the interactions of HX, HA split like that. So basically it's a doublet. It's a doublet splitting. Then we have understood doublet very easily, fantastically. Now just we'll memorize something that will not go to that part of splitting for question purposes. So how Hx is one proton, then Ha will have one more C, mean 1 plus 1. That should be doublet. Number of protons plus 1, signal, number of signal. Only one proton is there, then only one proton plus 1. That's the origin of doublet. Origin of doublet. Okay. Now we'll discuss the origin of triplet. Let's say these compounds. We have two protons here. Let's say this is X, HX. These two are equivalent, that we have designated them as same as HX, and this is HA, and we have two methyl protons. Now, just from the simple calculation, if I say what will be the multiplicity of this HA as the nearest number of proton is 2, that it will be triplet. Now, here as we are learning, then we'll try to explain why it comes as triplet. So we'll proceed as we did earlier, similar way. Let us consider there are no interactions between Hx and Ha. So this will appear as Ha. We have external magnetic field here. This is, as I told, the number of protons can be told from the intensity. Though didn't mention the part intensity, but yet here I am mentioning intensity as well integrations. So this is basically 2Hx protons, and this is 2Ha protons. Ha. Ha. Just we are not putting as the standard values. You should remember. Just we are trying to show that this is going to interact with this. That's why we have put it closer. We are not explaining this or just writing this in terms of the exact value. This is not in scale. It has been put here just to explain the interactions. Now, what will happen here? No nuclear interactions. Interaction means nuclear interactions. No nuclear interactions between Hx and Ha. Then what will happen if we consider the interactions? We have external magnetic field B0. So if we don't have any interaction, then it would supposed to come at same value. Here what we have, this is Hx, 2Hx. Then we have two nuclear spin that align together. So basically what this Ha will experience, this will experience B0 plus these things. Magnetic field from Hx plus another magnetic field from Hx. You understand clearly, right? Two protons, that's why two magnetic field. So here splitting will be quite higher. This is basically B effective. Be effective in this case. So we will have Ha here. This is Ha. There will be another possibilities. B0 means here this is 2Hx case. One proton align these sides, means one nuclear spin align these sides, and another nuclear spin align these sides, means they are cancelling each other. Basically it means that now Hx do not have any effect on Ha, because here the inherent magnetic field are cancelling each other. So basically, yeah, sorry for interruptions. I had some calling, that's why. Right. Okay, so basically where the proton will come here, means here no interactions, no interactions. Why? As the nuclear spin of 2Hx cancel each other. And what with the case here? B0, we have Hx here, 2Hx, look the case. So basically means both the nuclear spin is aligning opposing to the external magnetic field. So basically what Ha will experience here is for Ha will experience here external magnetic field minus, I should use this arrow of, it means that this negative, that's why I put the minus, magnetic field from one nucleus Hx, also from another nucleus because both are in opposite side. So, so it will be on that side from the center line. Just for technical purposes, I will explain later why I am put it smaller. So here, what is the effective splitting? Here, no interactions. Here we consider no interaction. So here the extent of splitting is same here. Because here is no interaction, here is no interaction. That's why look, these are on the same line. Here we just consider no interactions for our discussions, and we are seeing that yet there is no interactions because these two nuclear spin cancel each other. It do not have basically zero magnetic field inherent. Basically, it's a B0. So this splitting arises from B0. This splitting arises from B0. This splitting arises from B0 plus this. That's quite higher. And for this is B0 minus this. Okay, is it clear? That's why it's quite this side. So if we put together, what we'll get? We get this thing, and these things. Now, one interesting phenomenon I didn't discuss till now. Here, look, this is one way that it will be up, first proton up, second proton down, means nuclear spin, plus another possibility there, first proton down, second proton up, two possibilities. So there will be intensity, double intensity. Now if I sum up these, what will the resultant? The resultant, this is the first peak, this is the second peak with double intensity, this is the second peak with double intensity, and this is the last peak with same intensity. This is nothing but triplet. So now you are expert enough. If somebody asks you in anywhere, for example, in interview board or something more else, more fundamental question appears on CS and net or some places that we have this kind of triplets peak, and it has been asked that why they are like that. Then you can say, okay, these peaks is comes from such a splitting that is external magnetic plus nearby the magnetic field from neighboring protons. This added up. That's why here the energy level is quite higher. And the second one, it's only for B0 as the nearby two proton nucleus or nuclear magnetic field cancel each other. So basically, it's the same splitting like B0. And this one splitting arises from B0 minus 2 magnetic field. That is the lowest one. Here splitting is very low. That's the more fundamental description about the triplet peak. If somebody again asks, can you tell it some more? Yes. So this is for the such a peak where the nearby protons of two protons do not have any interaction. Exactly, this peak is from the splitting for same B0 value. That's the beauty of triplet splitting. I hope you clearly understand the triplet splitting and doublet splitting. After that, from the next class, after learning something, we try to explain the structure determination of NMR. Which kind of structure determination? Is it cis-alkene or trans-alkene? That I have explained in terms of infrared spectroscopy. Now we'll explain in terms of NMR spectroscopy. For example, is it axial form or equatorial form? We can explain it from NMR. These two are dash to MR. Then how can I explain it in terms of NMR? All kind of fine tuning we will learn in the next class. And in the next class, we'll together solve some problem using all the spectroscopic problem. I think I need 2 more classes for the sum up of these all three chapter and the problem discussion. Then I will put some assignment. You will do the assignment and practice this.